recording.
Hello everyone, I'm Pearson Tyler Guthrie with the Communications Project. This is Michael Finch. We have a third member who couldn't be joining us today, so it'll just be us two presenting. What we'll be talking about today is the implementation of the entire scheme that we have for communications. Currently we have our modulator, which is a trellis coded modulator, and currently we are measuring its success with a kind of rough branch metric unit that basically determines it's on the receiver side, and it determines distances between symbols that we receive. I will discuss our implementation of the convolution encoder. We will also be explaining how we select and generate the partitions for our signals. Briefly mention signal transmission, how we're modeling it currently, which is our additive white Gaussian noise. And we're going to talk about the future work that we'll be implementing in the next few weeks. Our current Simulink implementation has 4 QPSK schemes kind of going at once. We just as if we're taking a QPSK scheme and just sending it 4 of them. So it's 8-dimensional. We do that with the trellis coded modulator, which I'll show y'all momentarily, with X8 partition signal mapping, and has our current branch metric unit for measuring error. So this is our trellis encoder. It takes 8 bits as input. Takes 1 bit and puts this to the convolution UNO encoder. I'll show you that on the next slide, what that does. And it takes the other 7 bits and uses those, converts them into an integer, which uses this it selects a point within the partition. The partition is given by the convolution encoder. The convolution encoder actually outputs matrices. These matrices contain sets of coordinates. It's a 128 by 8. These bits select which of the 128 within the partition is selected, and it outputs 8 coordinates based on that. So the output of this device right here is 8 coordinates for our entire scheme, which he'll explain more later what that means. And the actual coordinates are based on the subset that is output from this convolution encoder. So this is our convolution encoder. It's rate 1/2, which means that it takes 1 bit and outputs 2. It does that based on these 4 states. A couple examples down here. If you're currently in state 0, 0, you can have 1 of 2 inputs, and based on that input, you get a certain output. W1 is one of our subsets, X1 is another one of our subsets. And so when I was talking earlier about it actually selects the subset, it just outputs an entire 128 by 8 subset, which is then we use, like I said, this other 7 bits to pick within that subset what our output will be. And of course that puts you in a different state for the next time increment. So what's really nice is during the simulation you can actually see it highlights which state it's in and which state it's going to. So you can actually watch it evolve in time while you're simulating it. So this is how we get extra information and output our subsets for selection. And here Michael's going to explain partition selection.
Yeah. So pretty much what we did is the first set is a regular Q. Basically what we're going to do is we're going to take a regular Q squared PSK. We're going to take a rotation of that, and then what we're going to do for each of the sets is we're going to use the Cartesian product. And what that does, right, the Cartesian product And what that's going to do is going to take this two-dimensional object and take it to the fourth dimension, and then again to take it to an eighth dimension. And then that will create our 8-bit stream, because each of these points represent, you would produce like a coordinate of 8 within a 8-dimensional space. And so the idea is then we take both of these 8-dimensional spaces and union them, and from that we create our partitions. So like the first partition would be like the first 128 of the 8-dimensional set of the first one, and so on and so forth. So that's more or less what the idea is, because then what we're going to do later on is we're going to try to maximize this for Hamming distance rather than Euclidean distance. Like initially, if this is like point A and this is point B, we would take those 2 points because they're furthest away from each other in the constellation. That's why we would pick these 2 points as part of the partition. But with Hamming distance, it's sort of like gray coding. So you look at the difference and number of bits, and that's how you would implement it that way.
So here we have signal transmission. It's actually rather simple. What we do is we take our 8 bits that we have, our 8 coordinates as determined by the partitions that we have selected, and we split them up into 2 4-bit streams, basically pairs. We pair them up. And for each pair, there's a real and imaginary component. We put that through added white Gaussian noise. Future work is going to include a Rayleigh channel, which Michael will explain later. So after the noise, we split it back into we get the real and imaginary components back out, and we output those coordinates, those received coordinates, after noise has been added to the next part of our scheme. So here we get an input of 8 coordinates, received signal, and here we have our subsets, x1, y1, z1, omega 1. We then basically just compare all possible combinations. So input, we repeat our input, so it's a 512 by 8. This, once it's concatenate these subsets, it's a 512 by 8. So then once we have, 512 by 8 minus a 512 by 8, then we square all of that element-wise, and then sum across, we sum across the 8 dimension. And so we get a 512 by 1 in basically Euclidean distances. We take the minimum, we find the minimum, and we take the index of the minimum. Then, once we have the index of the minimum, we do 2 quick calculations with it. We basically find what subset it came from by dividing by 128 and flooring it. So that's going to give us a number, since we're working from 0 to 511, that's going to give us a number between 0 and 3. And that's going to be exactly which subset we picked it up from. Then we multiply that number times 128 and subtract it from the index that we got to get the point within the subset. Anybody familiar with modular operations? This is kind of will be a little bit intuitive to you. So it's on the entire 512 row that we have. This will find, kind of rounding it to the nearest. This rounds it to the nearest 128, and then you have to find the integer that corresponds to how far in that subset it went in order to find out what coordinate you have. And so our outputs to this are subset point and subset choice. Subset choice is going to be a number from 0 to 3. Subset point is going to be a number 0 to 127. The results, these are the results of this scheme that we've implemented. Still running simulations, actually, running right now as we speak. But so far, I was able to get this out of it. Since this is just kind of our primitive Euclidean distance branch metric unit to determine the coordinates, the results aren't as good as our final implementation will have. Our final implementation is going to have the Viterbi algorithm, which will be a lot stronger, have a lot stronger results. Here we have, we don't get under 5 under 10 to the negative 5th bit error rate until 12, 13, 14 dB. We have, at 14 dB, we have almost 10 to the negative 6. We would like better results, and that's what our further work is going to hopefully produce.
Okay. So, as already mentioned, I'm going to be taking the partitions already, and I'm going to try to maximize them for Hamming distance. So, and generally what that is sort of like with gray code. You have like 0, 0, 0, 1, 1, 1, and then 1, 0. And you would take the 2 points that have the furthest bit difference in them. So I take 0, 0, and 1, 1 and send that rather than, because it has 2-bit difference. And that's better for a Riley channel because I just looked at this pretty much this morning, and I looked at this, Brant skimmed over this paper, and basically the probability bit error is proportional to the noise to the minus the Hamming distance. So that's more or less the motivation of why we would use Hamming distance over Euclidean distances from this relationship. And I'll be probably looking more into that. Okay. And then also what Satish has been tasked with do is to make a Viterbi decoder from the Viterbi algorithm, assuming I'm saying that guy's name right. But more or less, it's made up of three different like block units you can think of as branch metric unit, the path metric comparative kind of unit, and the traceback unit. The branch metric, what it does is it nothing more than takes those coordinates and either does soft or hard decision depending on what you're trying to do. So if you're using Hamming distance, it'd be hard decision. If we're using Euclidean distance, that'd be soft decision. And what that does is it tries to find, it does the equation that it runs, and then what it does is it keeps the index of where the like for example, if it found it finds the minimum of each of the partitions, and then what it does is it keeps the point or the index of where that's located, and then what it does is it compares it. And if it's like starting from the trellis and there's only 2 possibilities, then it kicks out the other 2 possibilities. So if hypothetically, if it starts from state 0, 0, and it can only go to the next state by either x1 or y1, then it's only going to keep those 2 points. It's not going to even worry about z1 and w1. And then when it gets onto the next state, it's going to pretty much what it does the same. So this like comparative, it pretty much like keeps the survivors and does all the kicking and decision. And then it does it again. It loops. It's pretty much a large continuous loop because then it goes to the next state. And depending on how long your length, because you can it depends on how many bit streams you're sending. So if you're sending 8 3 times, then your trellis is going to have 3 sections. So the idea is that we have to do this. We have to do this comparison 3 times. And after we do that, what we do is we pretty much trace back. We find the path with the each transition which had the minimum Euclidean or Hamming distance, and we trace back and we pretty much clear it for the next line of 3 intervals to come through, and that's generally what the trace back is. It goes through the minimum path in order to get back, and then it outputs whatever. It's sort of like a complement to the convolution encoder. So whatever the input is that caused a certain output, it does the exact opposite of that to recover whatever bit was sent in. If that makes any sense. Clear as mud, right? So, any questions? Yeah.
What are you calling the rough branch metric? Actually, that branch metric is exactly, I mean, you're computing exactly what you need. However, I think you're calling it rough because you're not really using the memory.
Right.
Right?
We're not using the convolution encoder to
Right.
its full potential.
Right, okay.
So it's sort of like a prototype. It's more or less just to get the job done right now.
But that branch metric is computed correctly and it's exact. It's not rough.
Right.
Okay.
Yeah. I'm sorry. I may have.
Poor choice of terminology.
Okay, but I know what you mean.
Yeah.
Yeah.
And that curve that you presented then is the curve for the uncoded system.
Correct.
Because you're not taking
Because
advantage
you're not using
of
the Viterbi algorithm. Correct, it's the uncoded. And then we're going to use that to compare with the coded later. That's the final result, I guess, or where it's leading up to. Any more questions? Dr. Chen?
Are you going to explore some way of changing the modulation scheme, or this is just confined with specific design on transcoding modulation?
Yeah, I think we're going to work with Dr. B's 8X scheme for now, and then if it's more or less we're giving like the state flow. I think Milt wants to utilize that on his dissertation maybe. So we're pretty much helping him figure out tools in which he can use. So he'll probably take what we've done and put onto his dissertation that way.
Other options for changing our modulator, or we could use a state rate 2/3 convolution encoder, input 2 bits, get out 3. Those are different kinds of things that we could do with it. Currently, that was just kind of step 1 in our completion of the entire scheme. So we're going to try to implement the Viterbi algorithm, and then once we have both of those, then we can start changing the modulator, which would then we'd have to remake the Viterbi algorithm to match up with that modulation scheme.
Zach, you have a question?
Yeah, just, are you going to move to like length 16 vectors? Because I just remember before a lot of the progress things were talking about working in 16 dimensions, not 8. Did you reel it back to 8 to get a full, something full, or?
I think it's one reason why is more or less if we can prove it with the 8 dimension. Dr. B has already had her dissertation, has all the research involved, so it'd be more or less comparing it with what she has to prove that it works, and then possibly it depends on time constraints and really on what Milton wants to do.
Let me address that.
Yeah.
I don't think they will go to the 16-dimensional quadrature phase shift keying.
Okay.
The main reason is that the number of points for that system is enormous.
It's like a few thousand or so.
It's 8,192. So it's too complex for them to try to implement. So the idea is to get the system working with a simpler one, which is my X8, which is in 8 dimensions, and it's not QPSK, it's just QPSK, which consists of 512 points. The expanded constellation is only 512.
Okay.
Yeah. But if you can do it with the X8, then obviously it wouldn't be very much of a difficult to do for the 16, if need to. Any more questions? Round of applause. Encore.